Yes.
Good morning, everyone. Thank you for joining. We'll be getting started in about 2 minutes. All right, thank you all for joining. David, I'll pass it over to you for introductions.
Hello, everyone. On behalf of my colleagues, welcome to this month's talk from the Johns Hopkins Institute for Assured Autonomy seminar series, a co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month, we host a talk on research topics at the intersection of assurance and autonomy. This seminar will be recorded. Today's speaker is Dr. Gopal Ramchurn. Dr. Gopal Ramchurn is a professor of artificial intelligence, Turing Fellow, and Fellow of the Institution of Engineering and Technology. He is a director of the United Kingdom Research and Innovation, the UKRI, Trustworthy Autonomous Systems Hub, and a co-director of the Shell Southampton Center for Maritime Futures. He is also a co-CEO of Empati Limited, an AI startup working on decentralized green hydrogen technologies. His research is about the design of responsible artificial intelligence for sociotechnical applications, including energy systems and disaster management. He has won multiple Best Paper awards for his research in multi-agent systems, energy management, and disaster response, and is a winner of the AXA Research Fund Award in 2018 for his work on responsible artificial intelligence. Today, Dr. Ramchurn will talk about trustworthy human-AI partnerships. Welcome, Gopal, and over to you.
Thank you, David, and thank you to everyone at the IA for the very warm welcome I received when I visited back in March, and for inviting me to give this talk. It's a real pleasure and honor to be here today. So good morning, everyone. As David said, I'm a professor of AI at the University of Southampton, and I run this large research program in the UK called the Trustworthy Autonomous Systems Hub. I'm going to talk today about my own research, my own views on trustworthy AI and how we build trustworthy human AI partnerships, and then go into some an overview of what the research program, the TAS, as we call it, the TAS Hub research program is about. Share my slides now. Hopefully you can all see that. And right. So before I go into a technical talk, and I know people will be busy and will be running off at the end of this talk, I wanted to highlight this opportunity that we've come up together So it's an opportunity to work with young researchers from the UK and the US. The first opportunity is what we call the Global Sandpit, which we're organizing in December. So if you are an early career researcher, basically an assistant professor or postdoc, you'll be invited to apply for that. It'll be an intense activity and intense research collaboration activity. And we also announced a defense call, so $1 million worth of research funds from DoD and the STL from the UK. And researchers from the IAA and from the UK are invited to apply for these from the Task Hub. So before I go into anything technical, I thought I'd highlight this. So please bear this in mind. And if you want more details, please contact David or Tony or Kara or anyone in the management team. They can share the link with you if you don't have it already. So, right, human AI partnerships. First, what I mean by autonomous systems and what kind of AI systems I'm going to talk about. Basically, I like to think of autonomous systems of all kinds. Autonomous vehicles that are driving around now on our roads, facial recognition systems that may be using historical data, maybe sometimes biased, to make judgments about who we are, what we may be up to. Predictive policing systems, so using historical data to figure out where things might be going wrong in our towns and cities. Or warehousing robots that are using some kind of sophisticated planning system, fail-safe mechanisms to guide, to work with each other, to carry things around warehouses. And many of these systems are now posing a number of problems for us. In their specific context, they raise important technical, legal, ethical, and regulatory issues. And this combination of issues, so the legal or the technical or ethical issues, render these systems sometimes untrustworthy. They may be trustworthy based on some of the fail-safe mechanisms built into them. So, for example, autonomous vehicles may have some fail-safes to avoid them crashing into each other, but they may not be trusted because they're designed in the wrong way or they're used in the wrong way. And the whole point of this talk is really, could we not anticipate these issues before they arise? And my point is really about what questions we should be asking. How do we sort of formulate those research questions to address this lack of trust and trustworthiness? So not being presented with a problem and then having to solve the trust question. So what we've come to realize, as with big tech and others, that too long we have focused on what machines do to us. So what I mean by that can be expressed in some of these questions. For example, can we build autonomous systems that do not break down in extreme environments? Can we build really resilient systems? Can we remove bias in data and in black box systems? Or can we protect the occupant's privacy in a smart home? So we build those systems, and then we think about, oh, how do we fix the privacy issue? Or how do we fix the bias issue? Or if they are operating in these extreme environments and they're going to fly and then, oh, they crashed. So how do we then fix those crashes or avoid those crashes? Again, another interesting, and keeps coming over and over again. So how do we hand over control from the vehicle to the driver when emergencies happen in an autonomous vehicle? Can we still maintain trust? So we're given this system, so we give the driver this autonomous system, and then we need to figure out how do we keep their trust in that system, or the manufacturer's trust in that system, that they've satisfied the regulation. Or what guardrails do we put around a swarm of drones? Again, we build the drones, we build the swarming algorithms, and then we deploy them, and then we think of the guardrails that need to be put around them to avoid them crashing in each other or flying over areas that they should not be flying over. Really, I'd like to think of systems as involving the participants, not just the systems on their own. So really thinking at the outset of the research projects, who the active participants in these systems are, who are going to be impacted by those systems, and therefore what are the consequences of machine autonomy. So you build these systems, before building them, you're thinking about the capabilities. What are the consequences of these capabilities on people's well-being, on society's well-being, on those who will use them, their skills, the way they will be liable for certain failures. So really summarizing that in one sentence, for me, trust is about what machines do with us. So as part of this partnership that we form with them. And I'll articulate what I mean by partnership through some questions. So, for example, we tend to ask questions like these ones. Does an autonomous car meet all the safety standards? Instead, we could ask a different question. Will my children be safe in the autonomous car on their way to school? And I'll talk a bit about what I mean by the other implications of that question. We design a breast cancer screening algorithm using machine learning, and we try to explain it. But can we use the results of these algorithms in a clinical setting? Who is responsible when we get it wrong? Or how do we reconfigure a swarm of drones, of uncrewed aerial vehicles when one of them fails? Instead, we could talk about how we support a swarm of autonomous drones and determine how we define who's responsible when they crash. So thinking about it more broadly. I'm going to go into a bit of more detail now on each of these questions. So the reformulated questions around the similar autonomous systems that I talked about. So if we look at the question of autonomous cars, so instead of asking about safety standards, and if you tell a parent, the accident rate associated to this Waymo car, for example, is 0.1%. So it's been driven around 30,000 kilometers and never crashed, or crashed once or twice. Will that give comfort to a parent? If it won't, then parents will probably not buy those vehicles, will never feel like they can trust these Waymo taxis to take around their kids to school. So when you open up this problem to the other issues, so when you involve the parent, you involve the stakeholders, the children, the parent, you need to start thinking about where this car will be deployed. Will it be deployed in a safe setting? Will it be deployed in a rural environment, on a motorway, on a busy road? Who will be responsible when the car is about to crash, right? Who takes over if it's children in a fully autonomous car? How does the parent feel in control of what's going on in that system? And I've been thinking a lot about this and thinking that, and it came to the conclusion that autonomous cars have been thought of in different ways by tech companies, by researchers, for a specific group in mind. They've been thinking of maybe the very rich Silicon Valley CEO who wants to be driven to work, or thinking of large trucks that need to carry lots of goods around. But manufacturers are really taking all these sort of techniques and approaches and applying them to general consumer cars. And is that the right way to go when these consumers are likely to have different concerns from those that specific user groups have? So really need to think broadly, and that will really help us address issues of trust in those technologies. The next example is one of smart homes. So many of these technologies, these Tado or Nest smart home heating systems, have been really designed for the tech savvy. They've been built for people who are used to using apps. They are built to mainly to serve potentially just one occupant sometimes. So I had one of these devices that would switch off the whole heating system as soon as I walked out of the house, leaving my whole family in the cold, because it used the geolocation services on my phone to decide whether it should heat the house or not. So all these systems actually transparent to other users like the elderly. So would grandma be safe in a smart care system that's powering this house? And really, we need to think about the implications here. So what happens when the system fails? What happens when the occupants feel unsafe? When power runs out on one of these sensors, are they still able to recover from these failures? Do we need other humans to step in? Do we need to think about the sociotechnical elements, not just the system itself? Not about it's less about, I would say, the machine learning solutions that you build into the systems. It's a lot about the human element in those systems. thinking here in this example on autonomous cars again, thinking here about a different perspective, not just the users of the system, but also those who will sell those systems to these users. So designers or builders of or manufacturers of these autonomous vehicles need to have some guidance to understand where and who to target with these autonomous vehicles. So will an autonomous car be actually bought by a certain group of consumers if it doesn't have a steering wheel? Or should you still have a steering wheel in there just in case they feel they need some comfort? Should you design it to look a certain way? Should it look friendly? And we found that consumers tend to like or trust vehicles that look a certain way, look safer, have rounder shapes or different colors potentially. So all these considerations come into play when deciding on what products to design. And this is a really crucial point when all these products are designed by self-interested, profit-minded car companies. They're not there specifically to just address safety issues. It's also about making sure that they can sell the right cars, but also getting them to think about the trust that the consumers will have in the system. The fourth and final example is one of drones. So we talk a lot about machines that can fly on their own, that can form swarms, and very rarely do we talk about the human teams that orchestrate the swarming of these systems. In many cases, these systems have failed, and if you can read some of these accident reports, they failed mainly because of the human team's failures sometimes. So one person in the room might say something that guides the pilot, guides some of the flight team to make decisions that end up crashing the drones. Now, these drones, the ones you see in the picture, were piloted or managed by a team of maybe 8 to 10 humans. Now imagine 100 of these drones flying together and having to be managed by a team of humans. How many humans would you need? How would you ensure that communication between these humans is effective and ensures that these drones don't crash into each other? So you can read the short accident report here. Humans tend to feel under pressure given time constraints. Humans need to communicate what they see in a way that maybe is too complex for their counterpart. So all these issues come into play when you try and build trustworthy swarming systems. And they are less to do with the autonomous system itself. They're more to do with how you manage the human-machine interaction, how you form the team, how you organize the team. And I'll show you a few examples of what I mean by orchestrating those teams. So in 2021, we wrote this paper on human AI partnerships, which builds a lot on the understandings we had of human agent collectives, of human machine interaction, lots of terms that have been proposed to define, to try and model or help model some of these problems that arise when you pair up very clever humans and very clever machines, and sometimes not very clever machines with not very clever humans as well. So we need to think of these systems as sociotechnical systems, not just technical systems. So think of the human element in there, where both machines and humans may be in charge at different points in time. It may not be obvious to us who's in charge, but they do take charge sometimes, these machines. And there may be algorithms taking charge or actual robots taking charge of the decision making for a group of humans, not just one human. We also look at humans and machines that cooperate, coordinate, but also compete with each other, particularly when these humans have their own self-interests, or machines represent humans or human organizations that have their own profits at stake. And in many of these large human AI partnerships, we're likely to see feedback loops that involve humans making decisions, producing data that machines consume, and machines in turn consuming and producing data that influence human decision making. And finally, in human AI partnerships, ethics and safety are primary concern at design time and at operation time. And we've seen a number of these human AI partnerships over time, and in the media, in the film industry, we've seen them, and we take them for granted. But there are some really good examples, and some really good examples of good human AI partnerships and bad human AI partnerships, where machines learn to behave in bad ways because we fed them the wrong objectives, or where where humans really work closely with each other. The one I like is the Knight Rider, where you have this real close partnerships where the human and the machine can help each other out, ask for each other's help, but also tell each other their constraints and challenge each other to do the right thing. So not just listening or just taking the human's needs and decisions as truth and as what needs to be done, but also challenging those, just to avoid going to suboptimal solutions. So I divide the concerns around human AI partnerships into three themes or dimensions. One is data, where we're concerned about learning, tracking, and reasoning about data. The second is about design. So we're thinking about teaming humans and machines, optimizing these teams, and explaining the behavior of the team or the behavior of individuals in those teams. And thirdly, it's a lot about incentives when we have self-interested agents, self-interested humans having to work together to deliver some kind of social impact. And here the concerns arise around fairness, arise around privacy preservation when you have humans involved in particular. So the question with data, when we have to decide based on data and learning, one of the key challenges I see in this area is one of positive feedback loops. When you have humans and machines feeding data to each other, feeding decisions to each other, and a good example of that is Netflix and many other recommender systems that do the same thing. If you go to Netflix and you ask, and you see the screen when you're not sure what to watch, Netflix will choose something for you, and it will keep suggesting things that are based on your own historical viewings, right? So if you've seen action movies in the past, it will propose an action. And over time, what it's only doing, and if you keep feeding back the same decisions, it will keep focusing you, narrowing your views down in a certain direction. So it's not really helping you learn. It's not really helping you diversify your taste or experience. And if you expand that problem to large systems of humans and machines, what could eventually happen, and we've seen this happen in some of the systems we've deployed, is this risk of oscillations. So you have interdependent or independent actors learning from each other's behaviors and causing each other's behavior to change very rapidly or shift very rapidly for no apparent reason. Another key concern around these large teams of humans and machines, as you're producing this data and you're feeding data to each other, is who is responsible at any point in time. For example, here you have a human and an uncrewed aerial vehicle teaming setting. You have humans on the ground, you have human controllers, planners, who are trying to coordinate large teams of these vehicles and humans at the same time. And they're making decisions in real time. They're making decisions with partial visibility of the environment, with partial knowledge of what's going on in the sky and on the ground. So who's responsible? And here we proposed solutions in the past that looked at tracking data and decisions, but you need to do this at machine speed. And when you're doing things at machine speed or at human speed, it's very unclear who's liable, who's really responsible, because obviously humans may think they're responsible for certain decisions, but machines may be reacting too fast, individually, also as a collective, because they can talk to each other much faster than we can talk to each other and tell each other what to do. So this is really, really difficult challenge. I've got a number of projects on that I try to address. So one potential solution is looking at using provenance tracking. So there are a number of standards now that have been proposed to track the provenance of human and machine decision making automatically, and then reason about these provenance traces, as we call them, automatically to figure out who is responsible, but also to figure out whether things are going wrong in these large systems of humans and machines. And here we could also apply causal reasoning techniques to figure out exactly, what are the causes and effects of certain behaviors. Next area of concern is around design. So how do we design systems of humans and machines when they're quite complex? For example, here this picture depicts a system we built that looked to solve for disaster response problems. So these are basically two OODA loops. I'm sure many of you will be familiar with OODA loops, where you have to gather the information, orient to it, and decide and act on the basis of that information. So in the context of disaster response, you gather data from a crowd on the ground, you classify this information, maybe using some humans, maybe using some algorithms, some natural language processing algorithm. You create tasks for your drones, and you can use humans to allocate tasks to the drones, or you can use machines planning systems to allocate tasks to the drones, and you can send out these drones. Once you've sent out the drones, you need to collect data, so to manage the data that's coming, those videos that are coming from these drones, and create tasks for your emergency responders on the ground. And these tasks can be created by humans or planning systems again. And then once you've allocated these tasks to either humans and machines, robots on the ground, you send them out, and then you need to keep iterating that loop, so that to ensure that the team achieves its objectives on the ground. And across this system, you'd like probably to track the provenance of decision and data in the system. Now it's a very complex system. It's very difficult to decide, how are we going to organize this system of human and machine to classify crowd reports? Are we going to have lots of humans reviewing what the machine, the NLP algorithms are doing? Are we going to have an algorithm that monitors the humans to ensure that the humans are labeling the data from the crowd? Similarly, when you're allocating UAVs to tasks, how do we decide on that? Obviously, a planning system will have access to sensor data, but humans might have a better understanding of the mission objectives, of the context on the ground, of the human needs. And once you deploy your emergency responders on the ground, it's quite a tricky balance of skills that you might need and might need to respond to very, very quickly, depending on the events unfolding on the ground. So creating these allocations of humans and machines becomes a highly complex challenge. So teaming issues arise, optimization issues arise, and obviously explainability issues arise, because as these systems are deployed on the ground, you'd like to make sure that, should new information be acquired that invalidates your previous decisions, you're able to justify, changes in your plans as well. So some of the issues we addressed was around, human operator to machine ratio, looking at how we vary those relationships. We change the organizational setup of humans and machines. So do we have many machines and small number of humans, or do we have one machine coordinating multiple humans? Also, how do we design these interactional arrangements? So who's in charge at what point in time? How do we trust the machine to oversee the humans, or how do we make sure that those overseeing the machines are actually making the right decisions? And at what point should they delegate control to the machines? So different modalities can be then of delegation could be thought of. And finally, as I said, in terms of interpretability and explainability, these are key requirements and key challenges too. And we proposed, for example, in some of the work on disaster response, and in other settings, maybe there are other approaches that might apply, but iterative approaches, user-centered design approaches are really key. Using agent-based simulation or digital twins to create virtual versions or simulated versions of the world, so that humans can test out different strategies, can throw different kinds of scenarios to the algorithms, could be helpful. These systems also need to be built by multidisciplinary teams that involve the highly technical experts, as well as those who understand the psychology of the humans involved, as well as systems engineers who understand how to bring these systems together. And a lot of it involves participatory design from the outset. It's not about building the drones or building the swarming algorithm and then thinking about how you're going to deploy it across alongside the humans. It's about thinking through these problems very early on and how they will be weaved into these human organizations. And we propose some of these ideas in that paper that I've cited here. The third and final element or area of concern is incentives. examples on the right give you an idea of the kind of challenges we'll be facing very soon, if not already. So when we have vehicles, for example, charging across the grid, across the power grid, each requiring a certain amount of charge at a certain time of the day to be able to drive off the next day or in the next 2 hours, how do we make sure that these vehicles don't overload the grid, right? And because obviously the capacity on your local distribution network is limited. So you need to make sure that these vehicles coordinate in some way to flatten their load on the grid. So when should these vehicles charge? And here you need to really worry about the owner's preferences. So can we really leave these vehicles to charge without any user input? I would argue not. You need to have them express their preferences somehow, and also manage those preferences, and ensure that the users feel empowered, and otherwise they may lie about their preferences. At the bottom here, you have an example where many people, issues of lying could also arise. So you would like to agree on a meeting time with someone else, and would you be comfortable leaving it to your personal assistant to decide on when you should meet that person, or would you want to control that and restrict the times? And we've seen a number of these solutions out there right now with the likes of Calendly, I think, where you open up your calendar to people and you restrict certain times. And very often what I find is that you open up many slots, but eventually get to cancel those slots because the system has obviously taken a slot that you were not happy with without your permission. So how do we model these preferences is a key issue in these large systems of humans and machines, and making sure that they preserve your privacy. So maybe they could learn your preferences while preserving privacy, and also minimizing your interaction with the system. If you have to keep going back to the system to fix it, it gets highly intrusive, and therefore could undermine your trust in those systems. In some of these systems, you need, as with the electric vehicles, you need to incentivize truthful reporting. And there may be different kinds of objectives you want to achieve with these reports. So maybe you want to maximize social welfare or fairness. So setting incentives for humans is quite challenging when traditional economics have been looking at very linear utility functions for humans, but we know very well that humans don't have very linear utility functions, and these change over time very often. So it's still an open challenge in game theory and multi-agent systems. And again, touching on that point to do with dynamic environments. So how can we cope with these changing preferences and changing system objectives? Because maybe sometimes the objectives of the system may need to change from fairness to resilience. So if there's a disaster in the city, you'd like to change the way you orchestrate the charging of vehicles in a city. So potential solutions involve looking at game theory, obviously mechanism design without money, or interactive machine learning systems, but still very much an open area of research. So I'm going to go through 6 examples. I think I have time to do most of them. I'm going to quickly whiz through those and then get to the task hub. So this is a system that we built a few years back, so about 6 years ago, for disaster response. And here I use this to really show how we go from designing a system as simply a system of humans and machines to one involving a human AI partnership. So when we looked at, as I mentioned earlier, we have this problem of allocating emergency responders on the ground. So how do we efficiently deploy teams of humans on the ground using a planning system? So it's just humans, couple of emergency responders on the ground being guided by a planning system to certain tasks in a disaster space. So the traditional technical solution to this would be to use a coalition formation algorithm with spatial and temporal constraints. So we wrote one of those. We applied some multi-agent Markov decision processes on this to account for the uncertainty in the environment. And in version 1, we deployed this algorithm in a real-world environment. So we had a mixed reality game where each emergency responder would get a task, and they could reject those tasks if it didn't suit them. And what we find, and this was based on, sorry for the mistake here, but was based on a simple model of reward in the environment. So the more tasks you get to do the higher the reward. What tended to happen though is that the humans were rejecting tasks because they wanted to work with certain partners. We were testing this system with students on campus, and it didn't work well. So it did work, but not very well. They kept rejecting tasks until they got the task that they wanted. So the planning system was simply sending instructions to people on the ground for them to do. So treating humans as machines effectively, and that doesn't work. So in version 2, what we redesigned the algorithm to account for human preferences. We looked at how humans, we learned how humans were pairing up in the game, and then reconstructed the algorithm to account for these preferences, to understand when they might be likely to reject certain tasks. And we deployed this on campus. This was the interface that allowed, in the version 2, allowed a human mediator to mediate between the algorithm and the humans on the ground. So it was not just about learning the preferences of the humans, but also mediating the algorithm's recommendations with those on the ground. So this interface allowed the operator at headquarters to filter out tasks that they didn't think were important, and to explain to the participants on the ground what was going on and to respond to their concerns. So it's a combination of algorithm design, interface design, and organization design that was applied here and effectively resulted in much better performance. We've since then looked at multiple parts of this problem. For example, how do you manage a swarm of drones that are gathering information, and they're all operating, as local optimizers? And then how do you do this with as few operators as possible, while growing the number of drones as much as you can? So we came up with interfaces that would allow us to capture the information on the ground from the drones in the same interface as the one used by the operator to organize the swarm of drones. So the operator could see where, on this belief map that you see on the right, where the drones were certain about what was going on, where they were likely to be positioned, and use that same interface to create points in the space that would allow them to focus the mind of the swarm, or to repel the swarm from certain areas that the operator didn't think were important. You can find more details in the citation below. Third example looked at how do we organize a team of humans and machines to operate a large swarm, and thinking about the various roles that might be needed to operate that swarm. So there may be analysts who are looking at the video stream coming from these swarms. There may be a planning interface to allow humans to see what is going on. There's a mission monitoring interface, a planning interface to allocate tasks and to coordinate with the algorithms that these drones are using, and a mission monitoring interface to create tasks and see where the tasks have been completed, to see where the drones have been in the past, and thinking more broadly about the organization that you need to bring together to ensure that the operation is carried out efficiently but also safely. Now, when you bring together large teams of humans operating in a high tempo environment, you obviously induce stress. So when they're operating under pressure, it's important to understand whether the team's performance is going to be impacted by the individual members' behaviors, or can we improve their performance by introducing software agents, planning systems to reduce the stress or to improve performance. And we did this bit of work in the middle of COVID, where we had to run things online, and found interesting results around how in teams of humans doing a simple task, which you can see below, so where you need to move blocks and coordinate in the way you move blocks on a simple Google sheet, and that sometimes the weaker team members weaken the other team members who may be very fast at doing this task. We also found that different kinds of communication modalities would allow them to perform differently to different levels. So explicit versus implicit coordination improves or worsens performance in some cases. The fifth example talks a bit about the incentives in these human AI partnerships, and particularly in power grids. And again, here you can I'll juxtapose two examples, one where we didn't account for the human AI partnership and one where we did. So in example one, design an algorithm that would control appliances in the power grid to ensure that we flatten the load on the grid. But unfortunately, what that results in is so significant disparities between different homes with different amounts of energy consumed. So in version 2, we fixed that and by looking at fairness objectives. So centralizing the decision making, not leaving it to the individual homes to run the optimization algorithm, and apply different fairness objectives leads to very different outcomes. And you can see, in terms of the uncertainties on the right, you can see the plots of the uncertainties in consumption when you try and be fair in different ways, whether you are optimizing for social welfare or whether you're optimizing randomly allocating energy to different homes in a grid. And that is a key issue when you're trying to deploy autonomous systems that will be adopted by all homes. You would not want the high energy consuming homes to be given more energy than low consuming homes. And in this particular problem was studied in Nigerian context, where many homes get shut down every day of the week. And it tends to be the low energy consuming ones. But if you apply a different objective, a different kind of optimization, you can ensure that everyone gets a fair go at the energy that's available on the grid. Last example is a machine learning example and a healthcare related one. I hope are suitable given that I'm talking to the Johns Hopkins community. And it's about explainable AI for high resolution images. So when we try and deploy these very sophisticated algorithms in a clinical setting, how can we make sure that these algorithms are still explainable and reliable? So we need to understand, for example, in pictures, it is slide images of cancerous tissues, which parts of these high resolution images actually indicate the presence of cancerous cells. This problem is a very common one across a number of applications, not just in healthcare, not just in cancer research, but also in geospatial mapping applications. So as the picture you see below is large. It's a large high-resolution picture of an area, and you'd like to pick out the buildings, you would like to pick out the roads, and make sure that the classification is correct. But most techniques right now look at labeling, humans labeling these very high-resolution images, or splitting them up and individually labeling them. What if you could label the whole image in one go, and quite a lot of these large images, and then leave it to the algorithm to figure out which parts of this image are actually indicative of the features that you're looking for, or the class that you're looking for. So really speeding up the classification problem. So this is a very quick video, hopefully that I can speed through. So basically we break up the original image into smaller parts. We put these batches, or we call them, in a bag, and then we extract features from these batches. Let's speed up a bit here. So you create features from each of these batches, and you aggregate them, and the technique involves using that to classify the whole picture again, and whether it's class purple or green. But the technique that we built allows us to go back and check which small patch actually resulted in that classification. So that's the use of multiple instance learning, recent paper that we published. And that's really key when you don't have the time to label each patch from the start. You only have time to label the large picture in the first place. So that's typically how it's done in cancer research projects, for example. Okay, key takeaways. So as I mentioned earlier, I think we should be focusing on what machines do with us rather than machines do to us. And I gave some examples of what I mean by these human AI partnerships, and really think ahead of time. So really anticipate and reflect on the consequences of these autonomous systems on individual, society, and industry. And a number of challenges I've enumerated today around the design and implementation of these human AI partnerships. As they scale, we're having this increasing risk of feedback loops that we need to break and account for, data and decisions made by humans and machines that need to be tracked and reasoned over, and interactional arrangements that need to be designed for large teams, organizations, humans and machines that need to work together, ensuring that they are verifiable and explainable to ensure they are trustworthy. And finally, designing them so that the incentives are set right to achieve the outcomes that you seek, whether it's fairness or social welfare. So there's no one-size-fits-all solution to the governance and regulation of AI. I think when we look at all these technical issues and social technical issues, we need to think broadly about governance and regulation. It may be in different sectors very differently as well. Okay, so that was the technical part of the talk. Sorry, I rushed a bit at the end, but I hope you got a bit of that. And as I said, there's a paper that talks a bit about these human AI partnerships in more detail. And also the work that we are currently doing in the Task Hub. So coming to the Task Hub. So what is the Task Hub? The Trustworthy Autonomous Systems Hub. It's a large program that aims to deliver world-leading best practices for the design, regulation, and operation of socially beneficial autonomous systems, which are both trustworthy in principle and trusted in practice by individual, society, and government. Now, when we talk about world-leading best practices, we look to build world leadership through collaborations with amazing institutes like yourself, and look to work with practitioners, policymakers to take out these best practices to the real world. Just a bit of background on what the program looks like. So it involves a hub that I direct, 3 responsibility projects, 6 large nodes, currently 12 pump priming projects. I think we've completed all of those now. We have another 8 that have been approved. So 18 projects have been completed, and a further 8 have given the go-ahead. So the total amount of funding in the program is £33 million over 4 years. It involves maybe now over 30 universities since we started, over 100 industry partners. Most of our projects, or actually all of our projects, involve at least one industry partner, and they are from diverse sectors, whether they're from defense or healthcare or autonomous vehicles sectors. And we've grown our funding in the last year or so with extra funds coming from DoD and the STL. And we're a highly multidisciplinary program, so we bring together the engineer, the scientist, the artist as well. I'll come to that at the end. And effectively, it's one of the world's largest research programs in trustworthy AI and autonomous systems. Just to give you an idea of the network, we have nodes. I mentioned the nodes on trust, responsibility, resilience, functionality, verifiability, governance and regulations, and security. You may recognize some of the PIs of these large programs, and the projects that we look at are distributed across the UK, across lots of universities in the UK. So, which is why we're such a large community. We've just created that community, and we're now in the second year, or finished the second year of the program. We're entering the third year now. And the themes that we've collated, so we started organically. So each of the nodes had their well-defined themes, as you see, trust or verifiability. We started the hub to try and coordinate all these nodes and also create our own projects and make sense of what these projects were going to deal with, but also steer them in certain areas. So we steered them to look at net zero as a key challenge, and also inclusion and a fairness in society as another big challenge. And we really promote our early career researchers or not promote, but support them to grow this research base, to grow their skills, and really take the lead in this research area. So while as these projects have matured, we've now got a better sense of the kind of research team. So it's hard to know what you're going to focus on when you start, which we started with a very open mind. And what we've seen emerge from the projects we've funded, we've bomb primed, all these research areas around task techniques, So trustworthy autonomous systems, techniques and mechanisms, public engagement with autonomous systems, human-machine interaction, responsible research and innovation, and governance. And there are here some of the topics that you may be familiar with. So we cover all of these in some of our projects and many more as we will keep going in the next 2 years. And the cross-cutting values across all of these projects. We ensure these projects look at human-centeredness. They think about responsible research innovation. They think about ethics and equality, diversity, and inclusion. So that's a really strong part of the program as well. So EDI, equality, diversity, and inclusion, has its own director, its own theme within the program, and ensures, for example, that all our projects have a balanced theme. For example, they have a good mix of gender or of disciplines or of career levels as well. Just a few examples of projects we have in train, and some have concluded, and there are follow-on projects from these. So human swarm partnerships in extreme environments is one that we just completed, but there's a follow-on project from that looking at explainable swarms. Argos looked at AI-assisted governance systems, so using agent-based simulation to help policymakers decide on certain energy-related or sustainability-related actions on the ground. Trustworthy human robot teams looked at how humans would trust machines to clean a hospital room, or how they would do surgery alongside humans. Working closely with guys in St. Thomas Hospital now to do this work. Caspar Explains looked at how we can get humans or children actually to trust a robot to learn new skills. We find that children are more comfortable with a simple robot if they have any kind of autistic on the autism spectrum. And in that context as well, we applied we did some work on causal AI to try and explain the behavior of the robot to the teachers, so they could trust the system could be deployed with young children. Trust Me, I'm an Autonomous Machine is really more of a creative kind of project, looking at developing narratives of autonomous systems, master narratives, working with the Design Museum and the Ruskin Museum. And finally, the last bit that is in progress is the work with the Creative Engagement Program led by Steve Benford, where we are looking at constructing an installation that would involve a robot looking after a number of cats. Sounds a bit fancy and crazy, but it's actually will help us study some key issues around human trust in machines, particularly when you delegate a machine the care of loved ones. In the UK, people really care about their pets, and particularly the cats. And there are really strong critical ethical questions around leaving the care of your loved ones in a healthcare setting, for example, so in a social care setting. But we can't test it out with the elderly in the UK, so we will test it out with cats. So yeah, watch this space. It will be hopefully live next year at our next All Hands meeting. But you can find out more on the Glass Theory website. So on this note, I'll conclude and just briefly mention, I leave these definitions here for you and for everyone to see, as we've been very often asked what we mean by trustworthy autonomous systems. And this is a definition that tries to encompass everything that's going on in the program, but obviously will not satisfy everyone. But I hope I've given you an idea of what we are doing, and I look forward to working with you. Look forward to engaging, broadly across your research program and networking you with our own community. So thank you again for your time, and yeah, I'd love to get some questions.
Hi, Gopal. This is wonderful. I really enjoyed your talk. I think you hit on a lot of very important points.
Thanks, Steve. I haven't seen the questions, so if there are any.
Looks like we might have lost David.
There are
There's
a few
questions in the Q&A section. The first one is just, what are your thoughts on Dolly?
Right.
Hopefully I'm saying that right.
Yeah. This is the typical, and there was another one this morning, a study run by someone looking at the scientists' fears of autonomous robots taking over the world. Apparently 30% of us scientists think that robots will one day take over the world and could pose an existential risk. I think DALL-E and such articles and stories of killer robots are exactly the kinds of narratives that confuse sometimes. And our scientists have been good at pointing out the failures with DALL-E, right? So if you plug in office worker, you get lots of men, white men, and it's pointing out the obvious failures in the data set or the biases in the data set. But the general public is not aware of potentially those sorts of bias issues. And I think that's where we can make a difference with our communities, is to try and engage the public and tell them about the kind of obvious mistakes that you can make when you build these systems. So DALL-E is I think is not a gimmick, but it's something that is being used to just get that sort of attention, that traction with the general public and just publicity, but not really something that's going to give us anything. At least for me, it starts that conversation with the public about bias in data sets.
Thank you. As a follow-on question from Jane, how does some of the work on trustworthiness for autonomous systems apply to other AI efforts which don't involve autonomy, but which have similar potential impacts on humans and society?
Yeah, that's a good one, because a lot of the work many of the team actually coming from a data.
I am so sorry.
Noise.
My agent connection went away. Sorry, go ahead.
Yeah,
No
yeah. So,
Go ahead, Gopal.
no worries, David. So the question was, how I guess in other fields or other sectors when autonomy is not a key feature, you still have some of these trust issues, right? So the other large research program that we're associated with is the Horizon Digital Economy Program. So Horizon looked at privacy, data, the use of data in online systems, and people's trust in those systems. So one of the early work we did was in collaboration with Horizon was on the NHS Test and Trace app. And in that case, people were asked whether they trusted the app, whether they understood whether the app was using some kind of automated system to decide on whether someone had been infected with COVID or had been exposed to COVID, etc. But people had, what that work showed that is that people make judgments about these systems just based on how it's presented to them, the information that they've got from or impressions they have from their own friends and sort of community, rather than from clear understandings or terms and conditions written in the app. So whatever you might write in your consent forms or terms and conditions will never be read potentially, or so people make their own beliefs or trust beliefs about these systems and develop their own understandings of these systems according to what others say. So in that case, for example, the system was not using any kind of algorithm. It was some human deciding, okay, the simple rules that were built into those. And it's very hard to distinguish between an automated system and an autonomous system. In many cases, an automated system could easily be a bunch of rules in an app rather than a fully machine learning driven system. It's very unclear right now where the trust issues would be significantly different, except in some systems like swarm systems. But we see a lot of crossover from traditional non-autonomous systems to autonomous systems, and we reuse a lot of that learning in the research that we do.
Thank you. There's also another question from TAC that says, first, fascinating body of work, and his students want to ask about how you calibrate your agent-based model. They feel that this may be challenging given the complexity of the way you simulate human decision-making.
In the case, for example, of the simulations we did of the power grids, so we simulated 26 million homes in the UK, for example, charging their batteries. or in the case of traffic simulations, which I know TAC is very interested in, we looked at traffic in Athens. So we used real data in a simulation environment. So we replayed the data, and we created simulated models of the vehicles to try that learn from the distributions that this data exhibits. And then we try and replicate certain situations with that data, and then sort of try and calibrate the parameters of the model according to that. We've done similar things with the maritime sector, simulating routes taken by vessels, or in power grids, we simulated homes and looked at how the homes would react to certain changes in pricing, and compare that, for example, with time of use tariffs that have been used for the last 30, 40 years in the UK. And we see similar behavior. So we try and match to those known behaviors as much as we can, learning from the distributions exhibited in the data.
Wonderful, thank you. I know we're over time, but there's 2 more questions from Kevin, if you have an extra moment. The first is, are you finding teaming and or trust differences depending on the topic? For example, driving, cleaning, cooking, suggesting policies, etc.
So the examples, I'm not sure what you mean by the examples. Let me check the question. So in terms of the trust questions that rise, right, if I'm teaming or trust differences depending on the topic, yes, we do find trust differences between in different topics, in different application areas. They're all, because every application has its own sort of sociotechnical elements or expectations from the users, or come with the users of this system come with prior beliefs about how they should operate. They draw their beliefs from what they've read in the news, and the criticality of the situation is something that we've also noticed. So a recent study we've done on operators of a machine learning system that's supporting a control room, an operator room, where they're looking at multiple screens, and the algorithm will tell them there's something strange going on, something dangerous going on in one of the screens. In that sort of environment, what we found, for example, that the humans are less likely to trust the recommender system if the situation is really, really serious. They're going to use their own expert judgment to decide on whether something is dangerous or not. So the criticality of the situation seems to matter a lot in that setting, but it may not matter it may be different, for example, in the context of a fighter pilot, sort of a fighter jet, right? So if the machine is moving at machine speed, would you really want the human to make decisions at split second level, right? So you'd want the machine probably to make those decisions. So the trust questions probably changes depending on criticality, depending on prior beliefs, depending on mental models that they form of the system. And we've seen that in a number of contexts.
Thank you. And we have one last question from Kevin. For a long time, the presumption was that robots would take away blue-collar jobs. But with the creativity of AI now, should white-collar workers worry more?
Yeah, so there's an interesting discussion going on I've seen on Twitter and elsewhere about whether machine-generated art counts as art, right, in art competitions. So clearly, and we also have a lot of work in that space. So we've got a lot of machine-generated art at the National Gallery in the UK. So we've got our own section there. So we also trying to engage the public with that discussion as to whether machine-generated art is actual art. Yeah, I think there are a number of jobs like that will change or maybe disappear, but I would say change more, because as I said in my talk, you have to reconfigure some of these jobs to better take advantage of these machines' capabilities. And that means reskilling the humans to work alongside those machines in different ways. So I think we'll create new jobs. And in some cases, we might need to create more human jobs to do something that a machine is taking over. For example, in planning systems, we might need to have more people employed to certify those systems. I think that's a big area where we're going to create a lot of jobs because to certify an autonomous system takes a lot of effort, takes a lot of skills, and takes a lot of time to create different scenarios to test out those systems. So maybe we'll be employing more people to test these systems, and also to work alongside them, and not just phase out some jobs that humans are currently doing.
Thank you. Are there any other last questions from anybody? Panelists, I can open that to you as well.
Well, Gopal, I would just like to thank you for coming and talking to the group, and also I was hoping you might sort of make one last pitch for the sandpit. Yeah. Just remind the 26 or so participants out there of the event, and there was a link posted, and which I can't write to the Q&A, but if we can make sure folks have that link, that would be super.
So
Yep, I'll repost it in the chat for everybody to click on. That's the first of the 2 links that I just sent.
Great.
Yeah. So just very briefly, the global sandpit, as we call it, the global sandpit, is being organized jointly with Johns Hopkins University, IAA, and the University of Texas at Austin, and the task hub. So King's College London, University of Southampton, and Nottingham University. So we are coming together to really create this new network of early career researchers, so young researchers, to by co-creating new research projects in a very intense 1-week activity. It's managed by a facilitator, professional facilitator, and it's got a budget associated to that. So out of that, of a £200,000 budget, we'll be funding travel, stay in different countries, workshop fees, consumables, etc. out of that budget. But really, it's about bringing researchers who already working in certain areas and want to make new connections and join up their research with people across the Atlantic. And out of that exercise, we hope they will go out and bid for larger pots of money from the NSF and EPSRC in the lead agency as part of the lead agency agreement. So that's the eventual goal. So helping those young researchers to build up their career through these very intense activities, where hopefully they will make some new contacts. The other call is the Agile Defense Call, which is really defense focused. It's led by DoD and DSTL. They are funding up to $1 million this year, could be more next year. So get involved now. And this is not just for early career researchers, it's for anyone really who has an interest in defense applications and is looking to collaborate with the UK research base.
Fabulous. So the sandpit, the next sandpit, December 12 to 16, if I recall correctly.
Yeah.
And contact Tony and or Kara to get engaged. We'd love to see a good representation from our community here. So thank you again, Gopal. Awesome talk. A lot of great topics.
All right. Thank you all for joining us today.
Okay, I think we're done.
Yep. We'll see you over in our breakout session for a few minutes.
Breakout session. Okay.
Yes.